So as you can see, if H is negative and S is negative, they're both the same, then G depends on temperature. If the temperature is really low, like 1 Kelvin, then it's spontaneous. As temperature rises, we hit equilibrium, and then as temperature gets even warmer, it eventually gets non-spontaneous. So if it's exothermic and delta S is negative, therefore it's becoming more arranged, then it depends on the temperature. It depends on the temperature. Okay? How about when H is positive and S is positive? That means it's endothermic, but we're becoming more disorganized or more rearranged. For example, let's say that H is positive 100 and S is positive 10. Okay, then we get the equation G equals 100 minus TS right here, which is 10. Remember, this is delta H right here, and this is delta S right here. Okay, and then T is the temperature, because it's going to depend on the temperature to decide whether G is positive or negative. Let's toss these numbers in here and find out. Let's say that the temperature is 1 Kelvin, really cold. Okay, 100 minus 1 times 10 for the delta S. 100 minus 10 is 90. It's positive, which means it's non-spontaneous, and we're at a pretty low temperature. Okay, non-spontaneous at low temperature. What happens if we increase the temperature? Now, let's say to 10 Kelvin. Well, now G is equal to 100 minus 10 times 10. Notice that minus 10 times 10, and 100 minus 100 is 0. So that means we're at equilibrium. We're at equilibrium, okay? At equilibrium, remember, G is equal to 0. And we increase the temperature from 1 to 10. Well, what happens if we increase it to 100 Kelvin? We really heat it up. Now it's 100 minus 100 T. Remember, this is T right here, and this is S10. 100 minus 1,000. Well, we're at negative 900. Now we've become spontaneous at high temperatures. Okay? Now, you can go through and you can memorize all this stuff, but I'm not encouraging you to do that. I'm encouraging you to be able to figure it out. If H is positive and S is positive, well, it depends on the temperature, and it happens to be non-spontaneous at low and spontaneous at high. How did I do that? By just tossing in some pretend numbers for temperature, for S, and for H. And then up here, if H is negative and S is negative, then it happens to be spontaneous at low temperatures, non-spontaneous at high. How did I do that? Well, I made up some numbers for S and H, and then I just pretended to go from a low to a high temperature. You should be able to do that in your head. You should be able to do that in your head. Okay? So G equals H minus TS, just in summary. To figure out what G is, you have to know what H is, what S is, and if they're opposite from one another, then you for sure know what G is. If they're the same as each other, then it depends on the temperature, and you got to put in some possible values, and they probably will give you that in a particular problem. Let's go to the next page. How about G and its relationship to equilibrium? Well, remember, when G is equal to 0, we're at equilibrium. When G is equal to 0, we're at equilibrium. But before we can relate an equation that has G and K in it, we've got to talk about G at standard conditions. Because that's all we've mentioned so far, is that at standard conditions, we can calculate G by saying delta G is equal to H minus TS. And we've said this is equal to H delta H minus T delta S at standard conditions. And that standard conditions are 25 degrees Celsius, 1 atmosphere of pressure, 1 molar solution if we're, if we have a solution. It's standard, okay? But what about G at non-standard conditions? What about G when we don't have a little circle up here? Well, we can calculate that too. And we can calculate regular G at non-standard conditions by saying that it is equal to G at standard conditions plus RT natural log of Q. Plus RT natural log of Q. Okay? R in this case is the universal gas constant, and it's 8.31 joules per mole Kelvin. Watch out for this, though, because 99% of the time you will find G in kilojoules per mole. which means R has to be converted to kilojoules as well. And then that's 3 to the left, 1, 2, 3, and it means that it's 0.008314 kilojoules per mole Kelvin. Watch your units, watch your units, watch your units. So when you toss R into this equation, it almost always has to be 8.314 times 10 to the negative third. T is the Kelvin temperature. And then Q, if you forgot what Q is, Q, remember, is what's called the reaction quotient. It's the same as K, except for it's not at equilibrium. So coming back here, R is equal to this, T is the temperature in Kelvin, and Q is the products' concentrations or pressures to the power of their coefficients divided by the reactants' concentrations or pressures to the power of its coefficients. Just like K, but it's not at equilibrium. Just like K, but it's not at equilibrium. So in this equation, remember, we're finding G at non-standard conditions. It's equal to G at standard conditions plus RT natural log Q. And so we take these non-standard conditions into account. Recall that delta G, this circle right here, at that circle, the concentrations are at standard conditions, which are 1 molar. So if the concentrations are all 1 molar, then when you take products divided by reactants, you have 1, maybe times 1 or 1 squared or something like that, divided by 1. And so Q is equal to 1. And so at standard conditions, this equation becomes G is equal to G circle plus RT natural log of 1. And remember from math class, what's the natural log of 1? Or what's the log of 1? Log of 1 is 0, right? And 0 times T times R, this term then goes away. And so then G is equal to G circle when you're at standard conditions because the concentrations are all 1 molar, or the pressures are all 1 atmosphere. Lots of examples using this equation in the next video cast. Lots of examples using this equation in the next video cast. Okay? So now what about G and K? We did this about non-standard conditions stuff. What about G and K? We've talked about this Q thing at non-standard conditions. What about at equilibrium? Well, remember at equilibrium, G is equal to 0. At equilibrium, G is equal to 0. So then also at equilibrium, Q is equal to 1. Remember, because at standard conditions, all the concentrations are 1 molar. So this allows us to take this equation and say delta G at non-standard conditions are equal to delta G at standard conditions plus RT natural log Q. G is 0 at equilibrium. Q is now called K, the equilibrium constant, because we're at equilibrium. And so we can replace Q with the letter K. And so we can say 0 is equal to delta G circle plus RT natural log K. Watch out for the units on this, though, like I said before, because G is usually given in kilojoules per mole. And R, remember, has to be in kilojoules as well. So make sure you're putting in 0.00831 kilojoules per mole Kelvin for that. Okay? And so solving this and rearranging this equation now, since this is equal to 0, bring G to the other side and fix the negative part, and you've got delta G circle is equal to negative RT natural log of K. And so if you know the equilibrium constant and you're at standard conditions, you can calculate G and find out if it's spontaneous or not. Or conversely, if you know G, then you can find K, the equilibrium constant, and find out how the equilibrium sits. Is it more products or more reactants, depending on what K is? So lots of examples using this equation in the next video cast as well. How do you just solve for K in this, though? Now, I understand I could divide by negative RT, but then I get this thing. Delta G divided by negative RT natural log of K. These go away, okay? So then I've got negative delta G divided by RT is equal to ln K. What do? Divide by both sides by ln? Oh, no, I can't do that, right? Remember, to undo a natural log, what I need to do is take E, because remember, it's really log-based E, to whatever power this thing is. And so K is actually equal to E to the negative delta G circle divided by RT. This is the exponent right here. Page 832 in your textbook, and this is the 10th edition once again, has a whole bunch of relationships for you between G and K. And I just want to bring this up here for you a second. If I'll zoom in on it, you can see that if K happens to be a really, really big number right down here, then you can see that G is going to be a pretty small number. Remember, that means it's fairly spontaneous. And you can see that it generally goes in order. The bigger the K, okay, the smaller or more negative G is. Conversely, the smaller the K value, the more non-spontaneous the reaction is as well. More non-spontaneous the reaction is as well. You can see that this relationship between K and G can give you just kind of an idea of, hey, if you got a really small K, it's not going to be very spontaneous. If you got a really big K, it's probably going to be fairly spontaneous. So K and G are interrelated pretty well that way. Lastly, watch your units, folks. Watch your units in this chapter. I just want to go through a couple of things about the units. Remember, H is measured in kilojoules or kilojoules per mole, delta H. S is almost always measured in joules. In the back of the book, it's in joules, joules per Kelvin. So be careful when you're adding these two things, like in this equation, G equals H minus TS. Watch the units, because these are going to be in kilojoules and these are going to be in joules, and you're going to have to convert one or the other. And since G is almost always given in kilojoules per mole, you're going to end up converting S from joules to kilojoules. Why? I think they do it just to confuse you. G is almost always measured in kilojoules per mole. Be careful of that. Make sure that the T is in Kelvin down here. And then remember, when you're doing this, G is almost always in kilojoules. And this R value here, 8.31, is almost always in joules. So stick it into kilojoules as well. 0.00831 kilojoules per mole Kelvin. You may just want to write that one down again to make sure that you got that right. K, remember, never has any units. It's the natural log, so it's really the exponent. And remember that the little circles above the G, S, and H right here, they mean that they're at standard conditions, which is 298 Kelvin or 25 degrees Celsius. Lots of examples coming up in the next video cast. But I have a little page to read to you on page 833 of your text that actually gives you some reasoning behind, hey, what is this delta G thing, and why is it important in any part of everyday life? This is called Chemistry and Life, and it talks about driving non-spontaneous reactions. Many desirable chemical reactions, including a large number that are central to living systems, are non-spontaneous, as written. For example, consider the extraction of copper metal from this mineral called chalcocite. This contains copper sulfide. The decomposition of copper sulfide to its elemental form is non-spontaneous. Notice it's a positive 82, or 86, I'm sorry. Because the delta G is very positive, we can't obtain copper directly from the reaction. Instead, we must find some way to do work on the reaction, to get gives free energy, some energy to shove in there to make that happen. So, for example, we can envision the sulfur reacting with the oxygen to form SO2 right here, and this is a negative delta G reaction. If we combo these two reactions together, then all of a sudden we end up with a negative delta G, and we can get copper solid out of that. In essence, we've used the spontaneous reaction of sulfur with oxygen to provide free energy needed to extract the copper metal from the mineral. Biological systems employ the same principle of using spontaneous reactions to drive non-spontaneous ones. Many of the biochemical reactions that are essential for the formation and maintenance of highly ordered biological structures are non-spontaneous. These necessary reactions are made to occur by coupling them with spontaneous reactions that release energy. The metabolism of food is the usual source of free energy needed to do the work of maintaining biological systems. For example, the oxidation of the sugar called glucose, which is a whole bunch of the, makes up a whole bunch of the food you eat, to make carbon dioxide and water, yields substantial free energy. Notice it's a negative 2,880 kilojoules, a big number right there. You can see that this thing, once it gets going, very spontaneous in the forward direction, very negative delta G. This energy can be used to drive non-spontaneous reactions in the body. However, amines is necessary to transport the energy released by glucose metabolism to the reactions that require energy. One way is shown in figure 19.19. It involves the interconversion of adenosine triphosphate, ATP, to adenosine diphosphate, ADP, molecules that are related to the building blocks of nucleic acids. The conversion of ATP to ADP releases free energy, negative 30 kilojoules, that can be used to drive other reactions. In the human body, the metabolism of glucose occurs via a complex system of reactions, most of which release free energy. The free energy released during these steps is used in part to reconvert lower energy ADP to higher energy ATP. Now, if you've taken biology before, you know that these interconversions between ATP and ADP are the things that give just about everything in your body energy. Thus, interconversion is used to store energy during metabolism and release it as needed to drive non-spontaneous reactions in the body. If you take a course in biochemistry, you'll have the opportunity to learn more about these remarkable sequence of reactions used to transport free energy throughout the human body. And there's a great diagram right here that talks about how glucose oxidation right here allows this ATP to ADP to take place and redivision. And then it gives energy, this free energy right here, to cause cellular development and give you energy to think, grow, jump, do everything that you want to do. So once again, you can see chemistry, the central science, central to the understanding, not necessarily driving, but one of the understandings to things like mineral production, making metals, and biological systems, driving the body. Free energy causes that to happen. So in the next video cast, you'll see tons of problems done with GHS, free energy. Glom onto those, grab onto those, become a good problem solver, become a good troubleshooter, become a good person with knowing your differences in units between G, H, and S, knowing the differences between the R's, because the R's have to be in the correct units, knowing how to solve for K, knowing how to solve for K using this equation with E, and if you don't know where E is in your calculator, finding that thing, knowing where these equations are on the crappy periodic table. Zoom in on these right here, and you can see that all of the equations we talked about thus far, are really available to you right here on this periodic table. You can see that we've got the S, products minus reactants, the H, products minus reactants, the G, products minus reactants, G equals H minus TS. We've got G equals negative RT ln of K, and then they put it in a regular log right here too. And then we'll find out that actually in electrochemistry, we can relate G to electrochemistry. You can see here's non-standard G is equal to standard G plus RT natural log of Q. And then they give you the old Q equals MC delta T equation, specific, or heat capacity equation, and then down here were some kinetics equations too. But a bunch of these are available to you right here. Get used to using this equation table to help you solve those things. Good luck with your thermochemistry problems.